Oh, hello, I'm Carlos Frajuca. First of all, I'd like to thank all the organizers for making this wonderful workshop. Well, I'm going to present now my working that we're going together with Fábio da Silva Bortoli, my colleague in the São Paulo Federal Institute, and Nádia Simão Magalhães, a professor in the São Paulo Federal University. Our work is the influence of deceleration in the shape of a star in the breaking index of pulsars. What's the breaking index? Breaking index is when the pulsar rotates, it loses energy. And because of that, the rotation frequency is decreasing with time because it's losing energy and the rotational energy is decreasing. And in the canonical model, this index is equal to 3, but experimentally, we always find a breaking index lower than 3. Then I'm going to show you some things. This is my abstract. The institution it's explain a little bit about the pulsar, some history. This is how some neutron star works. And this is our model. Let me hide myself a bit. And this is our model makes that the star is a sphere that rotates, and this is how the star deformates with the rotation. This is the coordinates on the surface. This is the Poisson ratio. This is the shear modulus. It needs to follow that equation. And we're going, and this is are the solutions for that equation below. And what we have done, we have assumed some values and give this result for the deformation of that rigid sphere. The solution is for the polar rigid displacement. It is gave for this equation here. Then we need some numbers. Then we find in the literature these numbers for this function of the shear radius. We can see that it varies a lot in the diameters of the sphere, and we adopt some numbers. This is also the Poisson ratio for the neutron stars, and we're going to adopt this position in the isotropic position, and the Poisson ratio then is equal to 0.5. Put that numbers in the equation, you're going to have the solution here. And there's the solution for the equatorial regions placements is given for this delta A equals to this number. This is how the density profile of the star changes. That's why we chose that model for the rigid sphere, because the density profile doesn't change much in the ratios of the neutron star. Well, this is the canonical model, and the breaking index is about this number here. This is the velocity, the rotation of the star, and this is a dimensional number, and this what you find here. This the breaking index is about the 3 in theory, that canonical model. It comes from these equations here. This is the energy, how the energy of the rotation energy varies with time, and this is how the energy is emitted from the pulsar. These two gets equal, then we got that equation there. And now we're going to increase in the inertial moment of the star another term, that is, this is deformation on the diameter of the star. We are going to keep on that number here. There will be another term here, another one, delta A squared here, but it will be very small and it's not considerable for these calculations. The variation time in the rotation energy becomes then this number here. Compare that with the emitted power. And then we got a correction that is that here. The omega dot here is this num. This is the canonical model, but we have this correction here. We still got the same power law, but we have a correction here. It's not exactly omega to the third, but we have another term here, this omega squared here. It changes this power law a little bit. But this number, it should be small because it's a small deformation on the radius of this sphere. This is our conclusion. There is a change in the canonical model. This correctly depends on the rotation, can be of the order of a few percent. Thank you for your attention.